10 kilovolts, we still need 10 kiloamps to go to 100 megawatts. And that is the challenge. And many people focus on high current aspect of superconducting applications, but voltage is a significant challenge for particularly aviation, because aircraft at higher altitude, the density of air is small. So if there is low density of air, makes partial discharge very common. So passion, there is something called passion minimum, if you are familiar with high voltage aspects, and that causes difficulties for electric aircraft. So that means we need to have a simple, flexible, and resilient designs for superconducting devices to make them suitable for electric ships and aircraft. So our Center for Advanced Power Systems, our group focuses on HDS power density, high power density devices. We work with multiple companies and other universities to work on superconducting cables, cryogenic systems, and also high voltage electrical insulation aspects of superconducting devices. Our lab particularly is built to make measurements of cryogenic temperature, high voltage measurements of cryogenic temperatures. So as I said, our focus is primarily helium gas. Why do we focus on helium gas cooling? So one thing is helium gas, because it is gas, we can go all the way from 4 Kelvin to whatever temperature we need to. Typically, most superconducting devices cool below 80 Kelvin. So we don't have to worry about phase change in this temperature range. Helium is gas all the way from 5 Kelvin up. So we do not have to worry about phase change. And enhanced superconducting properties at lower temperatures, going to lower temperatures, critical current density of materials as superconducting materials increase. This is an example. This is the temperature on x-axis, critical current on y-axis. As you go down in temperature, critical current density goes up significantly. So, ability to go to low temperatures as needed is convenient when we cool with helium gas. And larger temperature gradients allowed without phase change, as I said, because unlike other, for example, if I use liquid hydrogen, it is liquid at 20 Kelvin, 22 Kelvin, but it becomes gas at higher temperatures. With helium is gas at the largest temperature region. And that, because it is the same phase over a large temperature range, it allows us to integrate multiple HDS devices. We do not have to have dedicated cooling system for each device. For example, an electric aircraft will have superconducting motors, superconducting generators, and superconducting distribution system like power cables. You can connect multiple devices in the same cooling stream because there is no phase change, and increasing flexibility that allows us to have flexibility in operating system design or power system design, because if the same medium is used to cool multiple devices, you can place the devices wherever you need on the aircraft or ship without having to worry about finding place for also the cryogenic system. So we are not the only group. Even though we started a long time ago, there are several other groups work on helium gas as a cooling medium. For example, the HDS degaussing system that is already an application on ships uses helium gas. And electric propulsion motor for ship propulsion that was developed by American Superconductor in collaboration with others, 36 megawatt motor that was also cooled by helium gas. And there are several other programs that use helium gas as a way to cool superconducting cables or other devices. So just to quickly show you a hypothetical system with multiple superconducting devices, as you can see here, you have a cryogenic system, a with 4 kilowatts of cooling power. It is not uncommon now. There are many large cryogenic systems that have this type of cooling power. You can cool a motor, a cable, a generator, and then and many other devices before it has to be cooled again. So that means even though you have large heat loads, for example, I'm using 250 watts of heat load from the motor, 150 watts from the cable, a kilowatt from the generator, and 500 watts from each of the other devices. So all these devices can be cooled with a single stream of helium gas if we have sufficient cooling power. And unlike I showed earlier, it doesn't have to be in series. It doesn't have to be all in series. It can also be in parallel. The reason why we may have to use parallel connection is one is the temperature required for two devices may be same. Then if we use them in series, the temperature will be slightly higher for the second device. So we can use series some devices and parallel in some devices. So it is because of the large operating temperature range, we can decide how we want to connect multiple devices. As long as we have sufficient cooling power, the same stream of gas can be used in cooling multiple devices. So this is an example of a 30-meter long superconducting power cable that we built and demonstrated using helium gas as the cooling medium. As you can see, these are the terminations of the cables, and this is the cable. It makes a long loop and comes back and joins here as a 30-meter cable. And we use a Stirling system to cool, and this provides about 250 or 300 watts of cooling power around 50 Kelvin. And in the back you see there is 6 kiloamp DC power supply that is used to test the cable. So the cable was tested at multiple flow rates. The primary variable we have in cooling a device with helium gas is the flow rate, mass flow rate. And mass flow rates and the operating temperature and temperature gradient are related. As you can see here, current on x-axis, and this is delta T, means temperature gradient between the inlet and the outlet. So how much of the temperature of the gas is increasing when it cools a 30-meter long cable. If I use small flow rate, or 1.4 grams, you can see the delta T is 12 Kelvin. So the inlet gas is at 50 Kelvin, the outlet gas will be at 62 Kelvin. But if I increase the flow rate to about 4 grams per second, then it is around 6 Kelvin. But if I increase the flow rate to 8.6 grams, you can see it is 3 Kelvin. 3 Kelvin is small temperature increase across a 30-meter power cable when it is even if it is carrying 3 kiloamps. So the current did not affect the temperature gradient when there is sufficient flow rate. So our system allows up to 20 grams per second, between 10 and 20 grams per second. So as you can see, one cable can be cooled with only 3 Kelvin delta T. So you can use the gas to cool a second device, a third device, and fourth device until you reach a temperature that it is too warm. Then you have to cool the gas again with about 8 seconds. And we also tested a 10-meter long dipole HDS cable. It is a power cable made by Advanced Conductor Technologies. As you can see, the cable is really small. It is a twisted dipole, and it is, you see the terminations, and it's similar to the previous one. It was cooled with helium gas. You can see here the critical current we cool each pole of each cable in the dipole carried close to 5 kiloamps. So that means if we use both the cables as one system, one cable, we could go up to 10 kiloamps. It is it's not only carrying current, but if you see the temperature, when we went to about 4.5 kiloamps, the inlet the temperature of the gas is around 65 or 68, between 65 and 70 Kelvin. That means this cable, if I go to 50 Kelvin, would carry about 10 kiloamps each pole. So that it would be a 10 kiloamp dipole. So helium gas is definitely suitable if we have a good cable design and minimize the heat loss by good designs to cool power devices. And the reason I'm talking about the temperature gradient is the whole idea of cooling multiple devices with the same gas stream. Of course, so far I said as if it is easy to cool systems with helium gas. That is not true. I just wanted to show that it is possible, but there are challenges in realizing large helium gas cooled superconducting power devices. As I said, low heat capacity of helium gas, because helium gas has poor heat capacity. The only way you can use helium gas is by going to high pressures. So you have to increase the density by going to 20 bar. Most of the systems we use go up to 20 bar. And otherwise we don't have much cooling power in helium gas. So that means we have to go to large pressures, so the whole system has to be designed to withstand high pressure. So larger applications require, it is not only high pressure, large flow rates. As I said, the examples, the flow rate and temperature gradients are directly related. We need large flow rates. It sounds small, 10 grams per second it sounds a small flow rate, but actually for helium gas, even 10 grams per second is a large flow rate. Because helium doesn't have density, 10 grams per second represents a large volume. So obtaining large flow rates is a challenge. And the second challenge, which is important, is even if you go to 2 megapascal, that is 20 bar, helium gas has low dielectric strength. Means its insulation, its use as electrical insulation is not suitable for power devices. We have to have very good electrical insulation system design, and that is one of our focuses for last several years, because we have shown that we can use helium gas for cooling power devices. We started focusing on the dielectric strength aspect of helium gas. So to talk about helium circulation systems, so we have several. This is the system we use for the cable demonstration we showed before, and we also have larger helium circulation systems. As I said, one of the challenges in helium gas cooled superconducting devices is the circulation system itself. So we have built a system where we have 4 cryocoolers, and each one has its own heat exchanger and also its own circulation fan. Basically, this is, even though it's one system, it is 4 circulation systems working in parallel. So each one has its own fan, so it provides a flow, and then all the flows are brought together at the exit. So we have large flow. Because each fan can only push so much gas, to get large mass flow rates, we need multiple circulation fans and connected in parallel. And there are other challenges when trying to cool, when we try to cool large systems with helium gas. One is a flow rate issue. We already discussed, you can have 4 cryocoolers. Each one has its own heat exchanger. You have 4 circulation fans, so you can push more gas to get more flow rate. So you can connect them in parallel to get large flow rates. This system allows us to get large flow rates, but the pressure drop it can handle is the same, because they are in parallel. It can only handle so much pressure drop. By putting systems in parallel, you get more flow, but the pressure drop will still be the same. But if you want a larger system to fight the pressure drop in the application, you may have to connect think about two fans in series, in parallel, and another fan in series. We call it a booster fan. This is primarily to have more capacity to handle pressure drop. Applications, superconducting cables or motors, generators themselves generate significant pressure drop. Unless you have a system that can handle the pressure drop, you will not be able to get large flow rates. So this parallel and series combination is what is needed depending on the application. So as I said, one of the challenges with helium gas cooled devices is though in this design, and if I use helium hydrogen mixture, we can reach 35 kilovolts at 2 megapascals.
Last a few minutes.
And the sizes of this cryostat and the conductor are similar to what we use in critical applications. We can also build dipoles. We can use 2 single poles or 2 cables in one cryostat like the dipole we tested before, or we can use a coaxial dipole. We also have been working on superconducting dipole designs, dipole cable designs. I'll skip this. So you can design the dipole in multiple ways. For example, this is the central conductor that serves as one pole, and the ring of smaller conductors together, they all together serve as second pole. So this cable, because it's larger, has the same critical current carrying capacity as all these cables. And then in between the green circles you see are electrical insulation. Some other tubes, plastic tubes used as electrical insulation to separate the 2 poles.
Dr. Pamidi.
The benefits of a coaxial dipole is because the current is running in opposite directions, the field, the magnetic field extends. 5 kiloamps per pole, and tested it. You see, this is the central one, and then you see the outer cable in the picture. So that is the central cable, and this is insulation rings, and then the outer cable. In helium, when we work with gas, pressure is directly related to temperature strength. So we do at different pressures, and the maximum we go to is 2 megapascals. That is typically where we would operate the